welcome to today's video on the product rule. Now let's dive right in with an example of a product rule from calculus, which is the rule for taking the derivative of products of functions. So here I'm going to start with the derivative of x cubed times sine of x. Alright, so the first thing that we need to know about taking the derivative of a product is that it's not as simple as just taking the derivative of each piece and then multiplying those results. That is, that we can't just take the derivative and spread it through this product. Instead, the first thing we need to know is that taking the derivative of a product is complicated. Alright, so once we realize that, that'll put us on our toes and get us ready for the actual product rule. Now, the basic premise of the product rule is that we're going to take the derivative of one function and leave the other function alone. So in this case, I would start by taking the derivative of my first function, x cubed, which I'll write with prime notation. So there's the derivative of x cubed. And I'm going to leave my other function alone. I'm not going to take the derivative of it. And then we're going to reverse the process. We're going to take the derivative of the other function and leave the first alone. So here, we're going to leave the first function alone, x cubed, and we're going to take the derivative of the second function, sine. Okay? And finally, all we have to do is add together these results. All right, so there is the product rule, and all we have left to do is take these two little derivatives here. So at the beginning, the derivative of x cubed is 3x squared. Again, we're leaving sine of x alone at first. Then we're leaving on x cubed alone, and we're taking the derivative of sine. So the derivative of sine is cosine of x. So we end up with 3x squared sine of x plus x cubed cosine of x. All right, so let's formalize this with the formal definition of the product rule. All right, so the definition of the product rule is that when we're taking the derivative of f times g, what we're going to do is take the derivative of the first function, so f prime, and then we're going to leave the second function alone, g. And then we're going to add on, leaving the first function alone, f, and take the derivative of the second function, g prime. But again, our general mantra is that we're going to take the derivative of one function and leave the other function or maybe functions alone. And then do that for all the different functions and add together the results. And again, instead of saying f's and g's, I really think you should say things like the derivative of the first times the second. Even when I'm looking at this formula, I really think of the derivative of the first times the second plus the first times the derivative of the second. And using those words first and second can really help over saying things like f's and g's. All right, let's take a look at another example using the product rule. All right, so here we have the derivative of 3x to the 7th times e to the x. Now, the first thing again is just remember that products are complicated, so that kind of puts us on our toes and doesn't allow us to just take the derivative of each function separately and just multiply those results. Okay. Instead, what I want to do is I want to identify my first function, and little parentheses can really help here. So I put parentheses around my first function, and notice that I put it around that constant 3 as well. I don't need to separate that out as a separate function because I can just use the constant multiplier rule. And then e to the x is my second function. All right, now the second thing to help eliminate some of the mistakes with the product rule is to start off by using prime notation until you're comfortable with the rule. So here I'm going to do the derivative of the first, and I'm just going to write that as a derivative with a prime notation. So 3x to the 7th prime. Then I'm going to leave alone e to the x. Then I'm going to add on, doing the opposite. I'm going to leave 3x to the 7th alone. Okay, so leave that first function alone and take the derivative of e to the x. All right, so now all I have left is to do these two derivatives. So the first derivative, the derivative 3x to the 7th, is a power rule. The 7 comes down and multiplies to the 3. We get 3 times 7 is 21. X to the, and then we subtract 1 from the power to get our new power. 7 minus 1 is 6, so 21x to the 6th. We leave alone e to the x. and then we add on again, leaving alone 3x to the 7th, and then the derivative of e to the x, well, that's the simplest derivative there is just e to the x. So there we have a very simple product rule. Again, the basic mantra there is to take the derivative of one function, leave the other function alone, then add on the reverse procedure, okay, taking the derivative of the second function and leaving the first alone. But let's take a look at another example. All right, so here we have the derivative of the quantity 5x squared plus 3x times 4x squared minus 5. And now you may be looking at this and think classic product rule. Now, unless the problem actually says you have to use the product rule on this, I want you to remember this mantra about derivatives that you always want to simplify first. So here, if we remember that mantra of simplifying first, simplifying before taking derivatives, we actually don't need a product rule. Instead, we can start just by simplifying or FOILing, and that will get rid of a product. So we're just going to FOIL this out. So we'll get 5x squared times 4x squared is 20x to the 4th. Then we'll multiply out here. 5x squared times negative 5 is negative 25x squared. Then on our inside, 3x times 4x squared is 12x cubed. And finally, our last term, 3x times negative 5 is negative 15x. And now we don't need a product rule. We got rid of our product and we can just do the constant multiplier rules, our power rules, and our sum or difference rules. That derivatives don't go through products, but they do go through sums and differences, that we can just take the derivative of each one of these parts. So the derivative of 20 times x to the 4th, 4 comes down, multiplies by that 20, we get 80x to the 3rd power, again subtracting 1 from the power. Our next derivative, we get negative 25 times 2 is negative 50, x to the 1st. Our next derivative, the 3 will come down, multiply to that 12, we'll get 12 times 3 is 36. Subtract 1 from the power, get x squared. And finally, our last derivative, the derivative of a constant times x is just the constant, so we end up with negative 15. Now, you may be saying, well, I'd rather just do the product rule than do that FOILing, and then I still have to do derivatives, but if you do the product rule, usually you're going to have to simplify that anyways. So you'd actually end up having to do multiple FOILings and then multiple combining like terms to get the same answer. So again, we always want to simplify before taking a derivative, before resorting to using a product rule. The caveat, of course, is if the problem says use the product rule, then of course you want to follow the instructions. So let's take a look at another example. Here we have the derivative of the square root of x times tangent of x. Of course, if you want to, you can try to pause the video and try this example yourself and unpause when you're ready to see the solution. Okay, so our first step again is to kind of group and see what our two functions are. So we have the square root of x times tangent of x. So our first function is the square root of x. Our second is tangent of x. Now again, as we're starting, especially for your notes, it's good to write out some product rules with the prime notation. So I'm going to take the derivative of the first function, square root of x, leave my second function alone, and then add on, leaving my first function alone, square root of x, and taking the derivative of my second function, tangent. Okay, so here, the derivative of square root. In general, a square root sends two square roots to the bottom. So we're going to get 1 over 2 square roots of x. We're going to leave tangent of x alone. Plus, we're going to take the square root of x left alone and take the derivative of tangent of x, which is secant squared. All right, so there's our derivative using the product rule. So this is the correct derivative, but maybe you need to simplify it to satisfy a homework program, or if you looked it up in the back of the book, it's going to give you that simplified version. So in this case, how do we simplify this? Well, we have a fraction, 2 square roots of x on the bottom, and in order to add fractions together, we need a common denominator. Now that's our only denominator, so we're just going to multiply the second one by that same denominator, 2 square roots of x. But of course, we need to balance that by multiplying the top by 2 square roots of x. Now, once we do that, we'll have that common denominator of 2 square roots of x on the bottom, and that will allow us to add our tops to our tops. So in our first fraction, we just have tangent of x, and then plus, what about in the second fraction? Well, this 2 squared of x will multiply together with this square root of x, and we'll get 2 just from our number, and the square root of x times the square root of x is just x. Finally, we have that secant squared, which isn't doing anything, it's just sitting there. So we end up with tangent of x plus 2x secant squared of x all over 2 squared of x as our simplified result. For our next example, we're going to take a look at a general product rule. This is where we're multiplying more than 2 functions together. So in this case, we have 3 functions. We have 7x squared times e to the x times a third function sine of x, and we want to take the derivative of that triple product. All right, now this is where it's helpful to just know the general idea of a product rule. And the general idea or mantra is that we're going to take the derivative of one function and leave the other functions alone. So here I would start off by just taking the derivative of 7x squared, which is 14x, and then I'm going to leave my other 2 functions alone. E to the x, sine of x, they both just sit there. And then I'm going to repeat for all the different functions in this product. So now I'm going to take the derivative of my second function, e to the x, okay? And the derivative of e to the x is e to the x, and then I'm going to leave my other 2 functions alone. 7x squared and sine of x, again, they just sit there. And of course, we're going to add these results again. And now all I have to do is continue until I hit all my functions and all their derivatives. So now I'm going to take the derivative of sine of x. Well, the derivative of sine of x is cosine of x. And again, I'm leaving the other functions alone. So 7x squared e to the x. Okay, and again, we're going to add all these results together. So there is our general product rule, just using that general idea of taking the derivative of one function while leaving the other functions alone, and then going through all your derivatives and adding up the results. All right, let's see if we can apply that general principle to this derivative. The derivative of x to the fourth, e to the 5x, tangent of x, ln of x. And again, our general principle is that we're going to take the derivative of one function, say the first function, x to the fourth, we're going to get 4x to the third, but then we're going to leave the other functions alone. E to the 5x, tangent of x, ln of x, just sit there. And then we're going to move on to the second function, where again, we're going to leave our other functions alone. So x to the fourth is just going to sit there. And then we're only going to take the derivative of that second function. The derivative of e to the 5x is e to that power, e to the 5x. And then times our chain rule times a 5. Okay. But again, we're leaving our other functions tangent and ln of x alone. Okay. We move on to our next function, tangent. And again, we're going to take the derivative of tangent, but our other functions are going to be left alone. So x to the fourth, e to the 5x. Tangent of x, we're actually taking this derivative. We're going to get secant squared of x, and then leave ln of x alone. And finally, we're going to move on to our last one, ln of x. And again, we're going to add on, leaving alone x to the fourth, leaving alone e to the 5x, leaving alone tangent of x, and only taking the derivative of our last term, ln, which is 1 over x. Now, you will notice, unlike the other examples, I didn't use prime notation just because there's so many different functions going in here. I really didn't want to copy this equation over and over and over again. So while there are advantages to prime notation, there are also advantages to doing the derivatives on the fly. Namely, you don't have to recopy your equation over and over. And finally, I want to take a look at one more example where we have to use chain rules along with product rules. Now here, prime notation is very helpful because it does slow your mind down so that you can actually see these chain rules. So again, the general principle is the same, that we're going to take the derivative of one function, e to the 5x, and I'm just going to write that in prime notation. I'm going to leave my other function alone, sine of x squared. Now remember, sine of x squared, that is not a product, that is a chain. That x squared is sitting inside of sine, it's not being multiplied by sine. But now I'm going to do the exact opposite. I'm going to leave the first function alone, and I'm going to take the derivative of my second function. Okay, so now what I want to do is just kind of pause and think about these derivatives separately. So if I was only doing the derivative e to the 5x, just take a breath and look at that derivative, I see that chain rule. It's not just e to the x, it's e to something more complicated. So the derivative e to the power is e to that same power, and then times the derivative of that power. So the derivative of 5x is just 5, and normally I do put numbers in front of exponentials. All right, so now sine of x squared is just sitting there. Again, this e to the 5x on the backhand is just sitting here. And now, again, I just kind of pause, I take a deep breath, and I consider this derivative as its own little problem. And when I do that, I'll notice that chain rule more likely, and I'll think the derivative of the outer function is cosine. We'll leave that inner function alone. And now we'll multiply by the derivative of that inner function. And the derivative of x squared is 2x. Okay? So when you do start to see chain rules mixed in with your products or other rules mixed in with your product rules, the prime notation can really slow you down and help you think about all the rules that you need to apply when you're looking at these problems. And if you want to learn more about the chain rule or see more examples where the product and chain rule are mixed together, please check out my video on the chain rule. And as always, please take a moment to like this video and subscribe to my channel.